In section 4.3, we're going to be looking at right triangles and their trigonometry. So for acute angle A, in this triangle we are shown, this is a right triangle. So our cosine is going to be the adjacent over the hypotenuse. My sine will be my opposite over hypotenuse. And my tangent will be the opposite over adjacent. And we remember this from the mnemonic SOHCAHTOA. In this diagram, in case you forgot, this is the hypotenuse, this side is opposite A, and this side is adjacent. Now, we also have some other terms that you may not have seen before. So, SEC is the secant of angle A, and it is 1 over the cosine. So it is the inverse of that, so that is going to be the hypotenuse over the adjacent side. The cosecant of A is 1 over the sine of A, so that is the hypotenuse over the opposite side. And the cotangent is 1 over tangent, so that equals the adjacent side over the opposite side. So now we're going to see this in a right triangle. And so if this side is 8 and this side is 15, we're going to use the Pythagorean Theorem to find the hypotenuse. So that's going to be 8 squared plus 15 squared and the square root of that. So that is the square root of 289, which is 17 for my hypotenuse. Now, I'm going to be looking at angle theta. So 8 is going to be my adjacent side, 15 is my opposite, and 17 is my hypotenuse. So, to do all 6 trigonometric functions, the cosine of theta is 8 over 17, sine of theta equals 15 over 17, and the tangent of theta equals 15 over 8. Now, once I have those 3, alright, since my secant of theta is just the inverse of that fraction, it will be 17 over 8. My cosecant of theta, I flipped my sine answer, and then the cotangent of theta is 1 over 15. Just like we used when we were constructing our unit circle, we have some special right triangles, the 45, 45, 90, and the 30, 60, 90. So in the 30, 60, 90, our sides come in the ratio of 1, 2, and the square root of 3. And in the 45, 45, 90, they come in the ratio of 1, 1, and the square root of 2. So we can use these to find, for example, the sine of 45 degrees is going to be 1 over the square root of 2. But I can't have a radical on the bottom, so we're going to rationalize that, and we end up with root 2 over 2. For the cosine of 45 degrees, because those two sides are symmetric, we know that our answer is also the square root of 2 over 2. My tangent of 45 degrees is going to be my opposite over adjacent, which is 1 over 1, which still has the ratio of 1. In our next example, we're going to use a 30, 60, 90 triangle to find the sine and cosine of 30 degrees and the sine and cosine of 60 degrees. So I'm going to sketch a 30, 60, 90, and to remind myself of the ratios of my sides. So now, the sine of 30 degrees is opposite over hypotenuse, so that is 1 over 2. And the cosine of 30 degrees is the adjacent side, which is root 3 over 2. Now when I'm looking at the 60 degree angle, now the sine of 30 degrees is my opposite, which is now root 3 over hypotenuse. And my cosine, sorry, that's a 60, cosine of 60 degrees equals 1 over 2. So if we know the measure of any two sides of a right triangle, or the measure of one side and one of the acute angles, we can determine the measures of all the sides and all the angles. This process is known as solving a right triangle. So, for example, we're going to solve right triangle ABC when the measure of angle A is 35 degrees and length AB is 10. So the first thing we're going to want to do is solve for this side, lowercase a over here, because it's opposite angle A. So what we have here is we know the side adjacent to A and we know the angle of A, so we can find the opposite side using tangent. So the tangent of theta equals opposite over adjacent, so it equals A over 10. So the tangent of 35 degrees equals A divided by 10, so A equals 10 times the tangent of 35 degrees, which when we put that into our calculator, we get 7. Now, we're going to want to solve for B, our hypotenuse, and so now we can just use our Pythagorean Theorem. So we know that 10 squared plus 7 squared equals B squared, so that is 100 plus 49, and that equals B squared. So B equals the square root of 149, or approximately 12.21. We will sometimes use right triangles to solve for angle of depression and angle of elevation. So the angle of depression is the angle by which an observer's line of sight must be lowered in order to see an object. And the angle of elevation is the angle by which an observer's line of sight must be raised in order for the observer to see an object. So we're going to use this example down here. In Snowbird, Utah, Jasmine enjoys skiing down a run that has an angle of elevation, so that's up from the horizontal side, of 20.2 degrees. Its vertical drop is 2,900 feet. And we're going to estimate the length of this run. So we know one angle, we know its opposite side, and we're solving for the hypotenuse. So if we know the opposite, and we're looking for the hypotenuse, and we know the side, the function that goes with that is sine of theta. And so we're going to plug in what we know. So the sine of 20.2 is going to equal 2,900 over the side I am solving for. And so then when I rearrange this, the length of the ski run is going to be 2,900 divided by the sine of 20.2, which when I put that into the calculator, I get that the length of my run equals 8,398.54 feet. Sometimes when we need even greater precision than just degrees, we will work in minutes and seconds. So a minute is 1/60th of a degree, and seconds are 1/3600th of a degree. One of the common places this is used is in latitudes and longitudes. So we're going to convert our angle measure here of 85 degrees, 18 minutes, and 30 seconds into decimal form. And so that's what those little symbols mean. So what we're going to do is we'll start with 85, and then we have 18 60ths, and then we have 30 3600ths. So it's probably easiest to just put this in a calculator, and when you do, you get 85.31 degrees. Combining those last two concepts, if Mary is on a trip to Washington, D.C., and she sees the Washington Monument standing 1,200 feet away, and she wants to take a picture of the top, and that is an angle of 24 degrees and 49 minutes, we want to know the height of the Washington Monument. So we have an angle, we have the adjacent side, and we are solving for the opposite side. So what we're going to want to use is our tangent, because that equals the opposite over the adjacent. We're going to plug in what we know. It's the tangent of 24, and then, let's see, 24 plus 49 60ths equals 24.82, so that's what we're going to put in, and then that equals the height that we're solving for divided by 1,200. So rearranging to solve for the height, that is 1,200 times the tangent of 24.82, which comes out to be 554.9 feet.